Good morning, everybody. Welcome to soggy, grey Amsterdam Monday morning. I remember talking to a couple of you during the welcome drinks when it was still hot and it was very unusual weather for Amsterdam. Now we have the usual autumn weather for Amsterdam. So we have that settled. So today we'll talk about homology detection and benchmarking, a topic you should recognize very well by now. Just out of curiosity, so far, how do you like the course? Yeah? This last week I think I asked, and there was a bit of overwhelm and too much things happening at the same time. Is that better now? Yes? If not, come and find, sorry? So your background is computer science? Engineering? Engineering, yes. Yeah, so indeed, if you don't have a lot of biology in your background, then there's lots of biology flying past you. We can't get around that because it's bioinformatics, right? Because and all our problem cases come from biology, and biology is complicated. But it's getting better, I hope already. Yes, good. And so so the biology class that helps. The biology class, the Friday morning classes, they help. Okay, that's also good to know. So and to a greater or lesser extent, this is true for all of you. There's lots of topics going by, lots of new concepts, or concepts that you've come across before, but sort of went away slightly. And at some point, these things have to come together and start making sense again, right? And I hope you'll see that during the weeks, as more pieces fall into their place, these things become gradually better. As I said, if not, come and find us, right? You're not in this alone. You might feel a little bit alone at some moments, but we're here to help you. Okay. There's something else. Come back. Okay, so homology detection and benchmarking. Who read the paper? Oh, that's very good. Who didn't? Ran out of time, or you really needed a weekend? The weather was much better. I understand. Don't worry, we'll get through it. Okay, so you recognize, if you've glanced at the paper, you recognize this figure, and so these are different methods for homology detection. Right? So you recognize blast and side blast. There's SAM, PRC, Hammer, J search, compass, all different types of methods that do homology detection. And the key question is, how do you know which one is better than the other? That's the bread and butter of bioinformatics. Because it's bioinformatics, you could say it's about data, but data is pretty useless if you can't process it. So I'd rather think bioinformatics is about algorithms to do something useful with the data. But then there's so many algorithms, and how do you choose the one that's good for whatever question you were trying to answer? Right? So without benchmarking, there isn't much progress that we can make in bioinformatics. So that's why we put this concept very central in this first course for you. Okay, so, and I hope that makes sense. Even on the Monday morning. So, that's what I was just saying. A typical bioinformatics problem is the needle in the haystack problem. There's so many genes out there, and some of them are maybe homologous to the one you're interested in, and a few of those might have, or maybe only one, might have some annotations that are useful, that tell you something about the function of the gene you're interested in, and you need to find it. That's the needle in the haystack. If you want to score or benchmark your results, you need gold standard data. right? You need something to benchmark it against. If you don't know what a needle looks like, you can sort through haystacks till the cows come home, to keep it in the vein of things, but you're not going to recognize it. You might find hundreds of needles, but if you don't know what it looks like, you'll just toss it on the heap of discarded hay. You need to be able to recognize it. There's different ways to score, so we'll go through a couple of these things. There's measures, numerical measures, and there's different plots we can use. And different research questions require you to use different methods. So basically, if the question is why use a rock plot versus a precision recall plot, it doesn't make sense. We'll come back to that in a few slides. That really comes down to which research question you're asking, or what you want this tool to do. Right? Okay, and this is the paper. Okay, good. So, and I'll set out a little bit how this lecture is supposed to go. I'll give about half an hour introduction on benchmarking. Then the rest of the time before the break, I'll sort you guys into groups and give each group one question. There will be multiple groups on the same question, or four questions. It doesn't make sense to have 4 groups of 30 or so students discussing one question. One question per group, groups of 4, 5, maybe 6 people. And then after the break, I'll rearrange the groups so that there is people from each of the different questions in one group. Groups of up to 8 people and 1 or 2 people from each question. So you can actually exchange the answers and explain to the others what the answer of the previous questions was. That should take about half an hour, and then I'll have 15 minutes left at the end to wrap everything up. Yeah, makes sense? Okay. So the real question is, the question I'll be coming back to as an example, how good is your blasting? Right? So how would you know? You run blast, you get hits. What do you do? Okay, yes. So you can look at the structures, but that's already a few steps. You can do simpler things. What's the first thing you look at?
The E-value.
You look at the E-value. Why does that tell you anything? It
tells you.
E-value detects homology. That's close. It's the chance that you have a random hit. So you want this E-value to be very low. It tells you that it's not likely to be a random hit. So if you have 10 to the minus 150, that's very close to 0. So that should be a good hit. Is it a real homologue? Well, with 10 to the minus 150, yes, probably. But there's a huge gray zone somewhere between 10 to the minus 6 and 1 or so, where there's lots of homologues still hiding in there. And you might not be so lucky that you have obvious homologues that you have a structure of or any other functional annotations of. And you have to go fishing in the gray. That's, because I think the easy cases, they've been done already, usually. So if you're working on a problem as a bioinformatician, well, maybe today or tomorrow, or in a few weeks, or a few months, or a few years, it's likely that this is not an easy problem. Otherwise, you wouldn't be working at it. Somebody else would have done it. Yeah? So that means you're fishing somewhere in the gray zone. Okay. So I'm doing this, and then you really need to be able to say whether it's a real one. Right. Yes. That's what you're saying. And so if you're in this gray zone, you inevitably have a balance between finding true answers, finding a real needle, versus finding false answers, finding just more hay. And it's very easy to make a method that doesn't make errors. How will you avoid, you have an homology detection method, how can you make this avoid finding any non-homologs by accident?
Never find a homolog.
You just don't find anything. Predict 0, 0 error. It's easy. Yeah? You can take the other extreme and make a method that will always find you all homologs. How would you do that? It's equally easy. Where are all homologs? Yeah? Find everything, right? You take the whole database, you know for sure all the homologs are in there. Neither of these are very useful. Yeah, because it's like the needle in the haystack. You say, oh well, there's the haystack. Right? If the needle is in there. That doesn't solve your problem. Yeah? Or you just don't look at it. You haven't found any hay. You haven't found any. Okay. So there's always a balance. And to be able to quantify this balance, I have a very nice table here, just tossing at you. Here it says data. Why does it say data here? It's rather prediction, right? So you have a blast hit, which says it's. So this is what your method tells you, right? It's either below or above the threshold. This is your conclusion. Okay? Don't blame BLAST for finding something that's not a homolog. It was your conclusion based on the e-value. You think it's a homolog. Right? So this is your conclusion. Putative homolog or putative non-homolog. If it's above the threshold. Then database, your reference database, basically the same thing. Don't blame the database for when your classification might be wrong. You have whatever category you take, it could be PFAM, scope, or Go. You say that basically the idea is it's always something like if they're in the same category, they're homologs. If they're not, they're not. Right? But that's not what's in the database. Well, some databases actually claim that they group homologs. You should be able to trust them there, but it's also their claim, right? And it's on you to take that claim on face value or to apply some caution there. So if you say, well, if it's in the same category, then your conclusion is it's a true homolog. If not, it's not homolog. There are other options where your hit is not in the database, but you can't say anything. Or for BLAST, it doesn't really, well, you actually have that, where there's sequences that BLAST will not record because they just never get through the first filtering steps of the method. So it doesn't report an e-value. So there's no e-value, it's neither above or below the threshold, and you couldn't discard them, or you could say, well, then they're probably way above the threshold, and quite likely not homologs. I didn't put that row in this one. Okay, so do you all know about true positives, false positives, true negatives, and false negatives?
This is a question about what do you mean with a category in this context?
Category? Yeah. It could be a PFAM family, or it could be a SCOP. What's the lowest level? Families? I think so. Or a clan. SCOP clan.
Right. PFAM is the database, right?
PFAM is one of the databases,
yeah.
Yes.
And
So in PFAM, protein domains are categorized into families, protein families.
Yeah,
that's what PFAM comes from. And so this is then, the category there would be the same family. Right? If they're in the same family, they're very likely to be homologs. If they're in different families, they're less likely to be homologs. If they're in different, I forgot the hierarchy of scope. Families, clans? No, families, superfamilies, clans. If they're in different clans, they're very unlikely to be homologs. Yeah? But like with BLAST e-values, there's a gray zone there as well. If they're in different families, but in the same superfamily, they're still likely to be homologs, but you're not sure. Yeah? So there's always gray zones. But these categories you have to define in some way based on your reference data. So this is the real let's say that the crux of the matter in benchmarking. Anything. This is the example here is homology detection, but this will go for any bioinformatics method that you come across. Is that neither your prediction nor your data are exact. If you come from a computer science or an engineering background, then if you have a reference data set, a gold standard, or ground truth, you can typically assume that it is correct. Might not always be true, but it's typically correct. This is not so in biology, because we don't know biology. We're learning about it. That's the whole problem. Yeah? We don't know homology. We have data from which we can derive information about homology, but we haven't got the sequences of the ancestral species that went extinct. I don't know how long ago, or not extinct. Depends how you define species. But if they went extinct, then we wouldn't be looking at the current day sequences. But you get the idea. Right? We don't have those common ancestral sequences. We can't go back and check for sure. Okay. Good. Now, who doesn't know? Do you all know about true positives, false positives, true negatives, false negatives? Or should I go through them briefly? Should I? I'll do it anyway, just to be sure. Right? So a true positive is a correct prediction. Right? It's below the value threshold. I'm just using homology detection here as the example. And it's actually a homologue, right? Or it's actually a needle. It's a true positive. If you found it. If you find it and it's a needle, it's a true positive. Okay. A false positive is when you have a very straight bit of hay, but it's not a needle. Now you think, oh, it's a needle. Oh, no, it's yeah, that's a false positive. It looks like a homologue, very nicely valued, but it's not. It's off for whatever reason. Okay. A true negative is something that you have correctly identified as not being a homologue, or as being hay, right? You just say, oh, this is hay. You toss it away, it's not a needle, you're correct. And then the false negative is when you, oh crap, there was a needle, and you've tossed it into your big pile of hay. You have to go back and look for it. Yeah? That's it. That's a false negative. And Monday morning, I hope you can forgive me. I was sitting next to a guy in the train that was way worse than this. I don't even remember. Okay, so this is true positives, false positives, true negatives, right? And not all, but a lot of the methods that you will use to score the prediction accuracy of methods, metrics that you use to score the prediction accuracy of methods in bioinformatics will use a combination of these four numbers. Okay. Is this? Oh, cool. Yeah, I actually had the one that I thought it wasn't. This one is much nicer. It builds up. So things to remember, not putting the same slide in twice. All positives. That means all the real ones, all the needles or the actual homologues. That's the ones. Those are all the true positives, the ones that you actually got correct. Plus the false negatives. False negatives are actually positives, but you thought they weren't. You're wrong. Yeah, that's why they're false negatives. False negatives are positive. Those are the bits of, those are the needles that you tossed away before you realized that this shouldn't have tossed away. Okay, then all the negatives, that does all the true negatives, that's clear, plus all the false positives, the ones that you thought were needles but weren't, or the ones that you thought were homologue but actually aren't. Okay. Then we have all positive predictions. What's that?
True positives and false
There's true positives, yeah. So all the ones you think are homologues, including the ones that aren't. Yeah? So that's true positives plus false positives. Okay, fine. Well, I have a very silly example here, but you can use length of hair as a method to predict whether somebody is male or female. And it's nice because it works in a classroom. You can actually go around and have some idea of whether it's correct. It's nice if boss is here. He sees a very nice counterexample of a guy with long hair. And there's also girls with short hair. There's nothing wrong with that. Just to show you that a single metric is never always correct. And if this, like I had used this example 10 years ago when we only had 20 students, then you can actually count and do the oh, do you actually know what this table is called? The one with the true positives, false positives, true negatives, false negatives. It has a name in statistics.
Confusion matrix.
It's a confusion matrix, a confusion table, right? It can actually be bigger if you have multiple categories and so on, like if you predict protein secondary structures, alpha helix, beta sheet, or coil, then you have 3 categories, then it's 3 by 3. It's called a confusion matrix or a confusion table. Okay, good. There's lots of confusion to be had with this topic, so I'll not develop on it too long. But the key element is that it depends on how good the predictions are, depends on your cutoff. Right? And you can never get it completely right. So if you take my hair as an example, then I would say, well, anybody who has this length of hair or shorter would be a guy. That's a prediction, right? It's not any value statement. But you can take any cutoff and you have a varying score of being correct or wrong. Even if there is even a correct or wrong answer. This is a way to complicate it, example. Okay, but you get the point. We have these 4 measures: true positives, false positives, true negatives, false negatives. There's lots of fun you can have with these to score how good. These are just actual numbers, right? There's like 25 true positives and 5 false positives, and so on. We're interested in our fractions or rates because the actual numbers will depend on the size of your database or other things. So you'll go through rates, and there's a couple of them. So the true positive rate is the number of true positives, as the name suggests, divided by, what's this number? True positives plus false negatives. That's all positives, right? It's also called recall, coverage, or sensitivity. And I've put all of these in one slide so you can use this as a reference. Because different papers will use different things. So this is the easiest, coverage and recall are the most sort of intuitive terms for this, I think. If you think about your whole database and all homologs in it, you have your protein of interest, right? There's a number of true homologs in your database. And this measures how much of those you've actually found. It makes you be able to retrieve or recall or forward. Right? Then there is specificity, or 1 minus error, or true negative rate. I hope I get that right. That's the opposite, right? So that's the fraction of negatives that you've correctly identified. True negatives divided by the total number of negatives. Then we have error, which is the inverse of specificity, also called fallout or false positive rate. So this is the fraction of false positives, the number of false positives as in the fraction of the total number of, what's this? True negatives plus false positives. All your negatives, right? Okay. Then we have, right. So these are fractions of all the positives or all the negatives, and you also have fractions of all the predictions. And the prediction is always a positive. Well, depends. This is fractions of positive. Right?
Yeah, the false positive rate shouldn't be like true positives plus false positives. Like from all positives, how many are?
No, that's positive prediction
value. Yeah.
Yeah, that's positive predicted value, or PPV, or precision, or 1 minus error per query. So this is of all the ones that you predicted to be homolog, how many are actually homolog? Yeah? Or about of your small stack of needles, what fraction is actually needle and which fraction of that is still hay? Probably nobody of you ever did that, right? Actually going through hay and looking for me neither, but that's just fun. Okay. And then there's error per query, which is the opposite, right? So this is the fraction of correct predictions in your prediction, and this is the fraction of incorrect predictions in your predictions. Yeah. And as I said, which one of there's no true or wrong, right or wrong one to choose, but which one you choose depends on your research option. I think I need to speed up. Skip this now. So there was just an example of trade-off. So trade-off, right? I've already gone through this, right? It's very easy to predict all known cases, just predict everything to be homolog, and you have all the homologs. Right? Not very useful. It's also easy not to make errors. Just don't predict anything. Yeah? Don't predict anything, you never make an error. Well, you do actually, by omission. And it's important to realize that when you optimize one of those, you do that usually to the sacrifice of the other. Yeah? If you optimize your coverage, you'll sacrifice your precision. If you optimize your precision, you'll sacrifice your coverage. It's a very rare case in bioinformatics where you can get both of them perfect. If you do, the first thing you have to worry about is that you've been terribly overfitted to your training data. Okay. Right. So more measures. I don't want to go through those in detail, but I just want to have them here for you for reference. There's accuracy. There's balanced accuracy, which is basically the average of your true positive rate and true negative rate. That goes correctly. There's Mesh's correlation coefficient. You'll come across that one a lot in prediction benchmarking papers. And there's others. Yeah, these are just the ones that you find most commonly. Okay, where are we going? Example again. All right. Now, because these measures, because there's always a trade-off in these things. People typically don't just look at a single number for a cutoff and then say, oh, this was my true positive rate, this was my false positive rate, and so on. You actually want to explore this trade-off, right? So, and the way to do that is in a plot. So you can plot true positive rate versus false positive rate, and you can see at different cutoffs how many errors you make and how much coverage you get. And that's called a receiver operator characteristics plot. Yeah? It plots coverage versus error, or one specificity, or sometimes it plots coverage versus specificity. It's the same, it's just as one of the axes. You can also plot precision versus recall. So recall is coverage, so one of the axes is the same, but then instead of the error, you plot precision. Or you can plot coverage versus error per query, which you've seen in the paper. Yeah? Okay, so this is an example of a rod plot, where this is from one of my own papers, where we were scoring the prediction of interface positions from sequence. You take the sequence as an input, and you want to predict which positions in sequence are likely to be on the interface of your protein-protein interaction. In a rod plot, so the random line is a diagonal. If you just randomly draw examples, then you have an equal chance of getting a true positive and a false positive, because it normalizes by the total number. And if you get a perfect method, you go straight up to the top right or top left corner. So because you make no errors, so this one increases all Yes. So it's important to realize that if you have most methods have a threshold. In this case, this was a random forest method. Random forest generate basically probability. The output is a probability of your answer being positive or negative. So the default cutoff is 0.5, but you can make it more strict or less strict, and then you get different predictions. And that's what happens if you go along this curve. Because this is a bit abstract, there's a very nice website. There's many, but this is one that I picked up. Yes. Okay. So you can actually go and have a look at this website and then do it at home. And bigger. Yes. Good. So if you have a score from your method and your positives, the blue ones, have a certain distribution in the score, it could be e-values. And the negatives have a lower, have a distribution that's slightly lower. This is what you hope to have, right? And this can be very different. Then, if for any given threshold, you'll have a mix of positive, true positive and false positive predictions. You can change the threshold. This is your rock plot. So the rock plot doesn't change, but the point that you choose on your rock plot changes. Make sense? So the link is in the I haven't uploaded the slides yet, I realize now. But you can play around with this. And if you are not so lucky and your let's see, the variance of your false predictions is much higher, you can see that the overlap is much bigger. Right? And then you're not. It's very hard to get good predictions because of the overlap. Yeah. Okay. Good. Then we can go back to this. Almost. Okay. Now, this is the same. Faster, guys. Yes. So this is the same plot, same data, but now we plot precision recall instead of the log. You see that the previous one, the red curve was at the top. That was my method. This is somebody else's methods. And the nice thing is that actually the difference is much more spectacular. What have I changed here? Because you can go back to this one. But well, this is also clear difference. Right? So what have I changed? So here it says true positive rate, which is coverage on the vertical axis, or recall. And here we have recall on the horizontal axis. But now instead of the false positive rate on the other axis, we have precision. So what was the difference between precision and false positive rate? Saying this correctly. Yeah, they've swapped. I'm now sorry. Because it says precision here. I'm just. Oh yes, precision. Yes. Okay. So this is the fraction of. So this is positive predictive value, right? So it's the. Sorry, I now because I was thinking too hard. I didn't listen carefully to your answer, so I don't remember exactly what you said. Can't think and listen at the same time. At least I can't. Yes, so this is the fraction of predictions, positive predictions that you got correct. This one can actually go up and down, because you can get the first one correct, and then the second one is wrong. So the first prediction is 100% correct. Your second prediction is wrong, so then both of them together, we're changing your threshold. Now you have two predictions, one of them is correct, the second one is wrong, so you drop to 50%. And then the third one is correct again, and so on, right? So then we go up and down. Okay. So here you can compare them next to each other. This is what I just explained. Good. Now, in the paper they used not the rock plot, but coverage versus. Oh, yeah. Some of these terms are used differently sometimes. So what I wrote on the slide are the most commonly used phrases. Precision and accuracy, I would always avoid using them because they are interpreted in different ways sometimes. But then the precision recall plot is always called precision recall plot, so people know what it is. So that makes it hard to avoid precision as a term. Yes. So the precision, as I use it, is the positive predictive value. So the fraction of positive predictions that are correct. So it's your true positive number of true positives divided by the true positives plus the false positives. So if you have 10 blast hits that score below your e-value threshold, 3 of them are actually homologs, the other 7 are not, then your precision would be 0.3. 3 out of 10. Okay. In the paper they use error per query, which is a slightly different measure. You should look up in the paper how they define that. Coverage is just coverage, that's the fraction of all positives that you've correctly identified. You can see that it's very good. None of these methods actually get halfway. They miss more than half of the known homologs. Okay. Yes. So I have 4 questions for you guys. And if you've reviewed last year's slides, you might recognize them. So, question 1 is, oh, sorry. Back. Okay. Doesn't work, it doesn't have a voice, but it does have a voice interface. Why do they use coverage versus error per query and not the rock plot? That's one question. Think about this. Then about the methods. How do they compare? And can you separate them into, based on their performance, can you separate them into different types of groups? Groups of different types of methods. Which database did they use? And was that a good choice? Might have used something better, different. Obviously different, but would that have been better? And then this is done on soluble proteins, cytosolid proteins. There's also membrane-bound proteins, and a specific type of membrane-bound proteins that actually go through the membrane are called transmembrane proteins. And so you could do the same method, the same exercise on transmembrane proteins, and then how would these methods compare? Would you get the same kind of performance with these methods? Okay, so these 4 questions, are they clear? Are there questions about the questions? Okay, then